All right, let's dive right into this explainer. Today, we're going to demystify the absolutely incredible journey of sound. We're exploring acoustics, which is this beautifully broad, interdisciplinary science that embraces the production, transmission, control, effects, and human perception of sound. It truly represents a synthesis of classical physics, engineering, physiology, neuroscience, psychology, and even architecture. We're taking a journey today from the microscopic dance of molecules inside a solid medium all the way up to the macroscopic design of cutting-edge Dolby Atmos studios.
So, if a tree falls in a forest and literally no one is around to hear it, does it actually make a sound? You know, it's a profound little riddle, but it perfectly frames the dual nature of acoustics we're exploring today. Depending on whether you view sound as a purely physical event or as a human experience, the answer to this age-old question actually changes.
So here's our roadmap for today. We'll be looking at objective versus subjective sound, the molecular dance, human perception of sound, controlling acoustic energy, and finally, perfecting the studio space. Let's get right into it.
Section 1. Objective versus subjective sound.
You know, sound actually has two completely distinct definitions depending on how you're looking at it. Are you measuring it with a piece of test gear, or are you perceiving it with your brain? Objectively, sound is a physical stimulus, a mechanical wave. And here is the kicker that separates acoustics from optics. Unlike light, which can just zip right through the vacuum of space, sound absolutely requires a physical, elastic medium to travel through. Without air, water, or a solid object, sound literally cannot exist. But subjectively, sound is a psychophysical sensation. It's the excitation of our human hearing mechanism that our brain then interprets and gives meaning to. Moving on to Section 2, the molecular dance.
To really understand how sound waves interact with our world, we have to look way down at the molecular level. Think of a material's atomic lattice not as some static grid, but as a super dynamic framework. It's basically a repeating grid of molecules held together by electromagnetic forces. When sound hits, three silent directors take over. First, elasticity acts like a microscopic spring. If you imagine a chain of three molecules, A, B, and C, and a wave pushes the middle one, B, out of place, elasticity snaps it right back. Then there's inertia. Inertia acts as the mass, and it actually causes that returning molecule to overshoot its resting spot, which triggers a continuous oscillation. Finally, we have porosity. This is the amount of open space in a material that allows air particles to physically penetrate deep inside, rub against the fibers, and actually burn off that sound energy as heat through friction.
So because a super rigid lattice, like steel, has extremely tight atomic springs, that restoring elastic force we just talked about snaps the molecules back almost instantaneously. To put that into perspective, just look at the difference here. Sound travels massively faster in dense, rigid steel. We're talking 5,900 meters per second, compared to the loose, tenuous molecules of the air around us, which clock in at just 344 meters per second. It's like a rapid-fire chain reaction. Tighter bonds mean the kinetic energy is passed along in the blink of an eye.
All right, Section 3, human perception of sound. Okay, so the fawn is a really fascinating concept because it bridges the gap between cold, hard decibel measurements and our actual subjective experience of loudness. Because our ears don't hear every frequency exactly the same way, scientists needed a unit that mapped physical energy directly to human reality. So the fawn anchors our subjective feeling of loudness directly to the objective pressure of a pure tone at exactly 1,000 hertz.
And that brings us to the famous equal loudness contours. Get this, our ears are significantly less sensitive to low frequencies, meaning if you want a low 50 Hz bass tone to sound identical in loudness to a 1 kHz tone played at just 30 decibels, you'd actually have to blast that bass tone at 60 decibels. That is a huge jump. It just goes to show that objective meter readings do not always line up with what we're actually hearing in our heads. Human perception totally requires its own distinct set of rules.
To bridge these two completely different worlds, acoustic professionals go through some pretty rigorous formal training. In programs like a B.Tech sound engineering curriculum, students literally map out these physical and psychophysical concepts side by side. They run practical labs on things like sound pressure levels and room decay times, often called RT60, specifically so they can learn how to physically manipulate a room to control our psychological experience of the audio. Which leads us to Section 4, controlling acoustic energy. Whenever a sound wave hits a boundary in a physical space, one of four complex physical interactions is going to happen. If the surface is rigid and flat, the wave simply reflects, bouncing back almost like a mirror image. If there's a change in the medium's density or temperature, the wave actually refracts, bending its path. If it hits a large obstacle, it can diffract, bending right around it like water flowing around a rock in a stream. And if it hits a porous material, it goes through absorption, where all that acoustic energy gets trapped and literally dissipated as heat. But we don't just want to absorb sound, we can scatter it too. The pioneer Manfred Schroeder proved that mathematically calculated irregular surfaces, called acoustical gratings, are absolutely incredible at diffusing returning sound waves. So instead of getting a harsh mirror-like echo bouncing off a flat wall, a diffuser scatters the sound in a million different directions at once. Because the grating has varying depths, it creates these complex phase shifts, leaving us with a beautifully rich, controlled acoustic environment.
And finally, Section 5, Perfecting the Studio Space.
So how do we apply all this to build the ultimate listening room? Well, to make sure a listener perceives a 3D audio space exactly as the mixing engineer intended, you have to follow some strict guidelines. A modern Dolby Atmos layout uses a 7.1.4 configuration. For rock-solid imaging, it's absolutely crucial to use identical speakers for the front, left, center, and right channels. And they need to be perfectly aligned horizontally, right on axis with your ears. On top of that, you have to maintain uniform electronic signal polarity across the whole system, so those mechanical waves arrive in perfect, unified phase.
Now, dealing with all that low-frequency inertia we talked about earlier requires a heavy hand. Bass waves carry a ton of physical energy, so studios use something called bass management. They implement an 80 Hz crossover filter, which basically redirects the heavy low frequencies away from the main monitors so they don't get completely bogged down trying to push massive waves. At the same time, the dedicated low-frequency effects, or LFE channel, gets a strict brick wall filter right at 120 Hz to make sure it doesn't muddy up the rest of the mix.
79. Specifically, 79 decibels measured with a C-weighted slow setting. That is the exact standard sound pressure level used to calibrate each main channel using pink noise in professional game audio studios. By locking in the subjective physical baseline, engineers can be absolutely confident that their highly subjective mixing decisions are going to translate perfectly when you load up the game in your own living room. To top off that immersive 3D bubble, Dolby actually recommends using discrete, physical overhead speakers for professional control rooms rather than those modules that bounce sound off the ceiling, simply because physical speakers offer way more precision. You want to mount these overheads at an elevation angle somewhere between 30 and 55 degrees. But here is the real key. To respect that speed of sound we analyzed earlier, coincident arrival time is absolutely mandatory. Engineers have to use digital signal delays to ensure that the mechanical waves traveling from the ceiling hit your eardrums at the exact same millisecond as the waves coming from the front monitors. It's wild!
So as we continue to master the invisible dance of molecules to build these flawless 3D soundscapes, it really makes you wonder, how will human perception evolve to hear the future of audio? Hopefully this explainer gives you a totally new appreciation for the invisible energy constantly dancing all around us. From the rigid atomic springs of steel to the complex psychoacoustics mapped right inside our brains, acoustics is just a phenomenal science. Thanks so much for exploring it with me today.